Hello and welcome to tutorial 1 of my C programming for beginners. So in this video I will introduce you to the C programming language and I'll go through a few things, and then we will finish off with 3 games for you to play around with. So first off, you're going to have 3 different ways to, two different ways really, how you can do this. So you can either download the CodeBlocks IDE, or you can use a C compiler in the browser. This is the one I recommend, and I use it myself for just testing small programs. So this will be fine for the first couple of videos where I go over some of the basics of the various commands in C. Although one thing I should point out is that my videos are game programming orientated, so I'm only going to go through stuff which I think you will be finding useful. However, I do recommend this site here. They have some C programming tutorials, so in between my videos you can always go here and have a read through some of their stuff. So if you do not want to use the C compiler in the browser, then I recommend you download the CodeBlocks IDE, the development environment which I will be using. So if I close this project here, this is the development environment that I will be using, and it is the same one that I use on Windows as well. So you can, if you're going to be going through my tutorials on Windows, then I recommend you going to my Windows install video and following that through. It's still relevant today, so you literally just go to the CodeBlocks site and then under downloads select the binary, and then you will want the min.gw setup here. That will be the one that is the most recent today. If you're on Linux, then I recommend just going to your software manager and then just downloading CodeBlocks from there. It'll probably be an older version, but it will definitely be easier than trying to build it from source code. I do have a video where I showed building the or rather downloading CodeBlocks from the command prompt here. Your best bet is to not try and build it from code, but to if you can either follow the Linux video, or just if you download from your package manager, then that should install the various things you need. So those are your 3 options there. The programs themselves, the links to them will be just in like a text file like this really. So you can copy and paste these. So you select all of that, copy that, and then you can just paste it in there and then run, and then that will be how you can kind of test this out. Or you can do the same in your IDE. So on Linux or Windows, so if I open it up on Windows and I just show it running there a moment. Just wait for the virtual machine to boot up a moment. There we go. So once Code Blocks is installed, then to open up one of the programs, it will just be a case of creating a new project and then copying and pasting it in. So my version on here is slightly older than the one that you'll have. However, if you follow the install video, which is still relevant, it has a different link for learning C in there. I don't know whether that link's still there or not. So all you would do is literally just create a new project, select a console application, make sure it's C, and then, as I said in the Windows video, create like a documents folder in your documents, maybe C tutorials or C development, something like that. Then give it a name, and then here make sure that you're only ticking the release one here. You have the GCC compiler set there, and your paths look like this. Then click finish, and then it will give you an empty start like this, and then you can just copy and paste those text files in. So if you select your text file there, copy and paste that in here, then save the file, and then build and run it. I think the virtual machine's acting up. So it will run. This is the virtual machine acting up, I believe. There you go. So this is the first program here. So that's how you can do it in Windows. I'll now show you everything working in Linux Mint, which looks very similar to what you'd expect on Windows anyway. So I'll get back to the tutorial. So what I'm going to cover today, so I'll go through a quick history of the C programming language. I mean, really quick. We'll go through how computers work at the basic level. This is just so you can understand what the language code, what it actually corresponds with on the computer, I guess. We'll go through, I'll quickly explain the types of computer memory. Then we'll go over some core computer data types. So as you know, computers pretty much just work with numbers. There are some sort of core number types, data types if you like, which aren't really kind of anything to do with C itself, although the computers, they only sort of understand these types. And then we'll have go through like C's equivalents to them. I've already gone through the useful links there at the start there. And then we'll get to the interesting parts where I kind of explain some of the basics in C. And then we'll go through some simple programs for you to have a mess around with. They're all game orientated. Like I said, the stuff I'm going to go over mainly is all going to be orientated towards games, stuff I use myself. So we'll go through the quick history of C here. So it's a general purpose procedural and imperative language developed in 1972 by Dennis M. Ritchie at Bell Labs. It's foundational for system-level programming widely in operating systems, embedded systems, compilers and real-time applications due to its efficiency and low-level hardware access. Basically, it doesn't take up much memory and it's fast. That's the takeaway there. So because it's fast and it can access the hardware of the machine, it's kind of it was widely sort of used back in the day, and obviously it's still useful today. So why learn C? Well, many modern languages, C++, Java, JavaScript, borrow syntax and concepts from it. That's just to name a few. Obviously there's C#, and there's D language, Rust, a few others. You know, they all kind of borrow some stuff from C. C++ obviously is based off of C. So learning C gives you a deep understanding of memory management, pointers and how computers work at a low level, making it invaluable for software engineering, systems programming and competitive programming. And more importantly for us, if you're watching this, then chances are you want to program on one of the consoles. So yeah, for us, we'll be using it for old games consoles. And the good part is obviously it's a single language, whereas if you were coding in C++, you're not going to be able to use that on the Game Boy or the Master System or the Mega Drive or the Super Nintendo or any of the other 16 or lower bit consoles, with the exception of like the Amiga and the Atari ST. So how computers work. So basically we have like a CPU. This is a schematic of the Game Boy here. So there's its CPU, the SM83, and it's connected to RAM there. This is where it can read and write memory, and it has ROM there, which is read-only memory. Oh, that's further down. I'll get to that in a moment. So the CPU contains millions of tiny switches that are either on or off. If you've seen like a picture of like a CPU, let's bring one up. So if we go for an actual CPU, so you can think of like all these. Well, the modern ones are kind of all look the same really, like that block there, so that's probably not a good example. Let's go for There we go. Now you can kind of see the different legs there. Things are the problem with learning now is you kind of need to go back to be able to go forward, if that makes sense. It makes sense to kind of start with the old machines because you can get a good understanding and see what's happening with those, whereas the more modern things, everything's kind of all packed in together, the different chips. So it kind of makes sense to when you look at these, if you look at like an old sort of computer circuit board. So let's go for okay, this is the Game Boy Advance here, but you can kind of see if I open that up in a new tab. You can see here that's where the actual CPU sits. There's its sort of RAM, and then everything's kind of scattered around more. So anyway, it's packed full of loads of little switches. These switches are what it uses to sort of count. So when you group these switches together, the switches are known as bits. They represent numbers when you sort of combine them into groups. So the number system that computers recognise with these switches is called binary. It's either these switches are either on 1 or off 0. So the one of the smallest sort of group, if you like, is called a byte, and then a byte consists of 8 of these switches. So these switches, so these bits here in the byte, so a byte consists of 8 bits, and they are labelled from 0 to 7, and they go from bit 7 on the left here to bit 0 on the right here. And then when these switches are sort of on and off, you kind of like toggle them off. You kind of add these numbers together. So if you add all of these, if all of these switches are on here, then that number represents the R equivalent of 255. And then toggling these on or off basically allows the computer to count from any number between 0 to 255 in a byte. And then if you need to go higher than a byte, then you have a word. And I'll go over these here. So there's different groups, and each of these groups hold larger numbers. So if you needed to store a number larger than 255 but less than 65535, then you might use a word. If you needed a number higher than 65535, you might use a D word. So basically these are just groups of bytes, if you like. These numbers here are consistently in force everywhere, so it's always 1, 2, 4, 8, 16, 32, 64, 128. So you see a byte can hold, a byte can hold 8 bits, and then a word can hold 16 bits, a double word can hold 32 bits, a quad word can hold 64 bits, and then they just go on up and up. I won't show you any more of the bit values here. So this terminology here, of note what I'm using here, this is the Intel assembly terminology. So if you're coding on assembly on a modern sort of desktop which is based on the 8086 chip, then this terminology is in force. However, if you're using a machine which is based on an ARM CPU, then they have different terminology. so they still have a byte, but they don't use the these sort of terms here. They use a half word for a 16-bit number and then a word for a 32-bit number. And this terminology you'll see if you're working on the Game Boy Advance or the DS, using like the Tonk library or the DevKit Pro library with the DS. They kind of have like some of the memory copying commands for like half word or word. So the numbers are used to represent everything on a computer. What I'll quickly show you a minute down here is this is the ASCII character set table here, the ASCII character set for the American and English. So any sort of English-based language will use this as its like standard sort of character set for our alphabet. So of note here is that if you wanted to output one of these letters or numbers in the terminal window here, so for example, just do a quick program here a minute. Okay, sorry, that should be 65. There you go. So you'll see that the value 65, when put into a char, this outputs the A character there. And then if you follow the decimal number here down to 65, you'll see the capital A there. I'll leave a link to this. Well, I'll actually leave this table as something you can sort of copy and paste. It's just a picture here anyway, which is very useful for when you're sort of working with characters when you're outputting stuff. I'll get back to that in a moment anyway. Another thing here as well to note is it also has a decimal column here, then it has an hexadecimal equivalent next to it as well, and then there's also a binary one here as well. This is octal, which is another number system which I've never used, so I won't describe it here. So you see here that you could even use this as like a conversion if you wanted to convert between decimal here, hexadecimal here, and binary here. Let's come back up to here. So I thought that was another little quick bit to put in there. So yeah, numbers represent everything on a computer. So old 8-bit computers, they typically didn't work with any 32-bit numbers at all, like the Game Boy, the NES, or the Sega Master System. They did have like a 16-bit register, which is basically, registers are kind of like onboard storage for the CPU, if you like. When it's kind of work things out, it usually stores things in a register first for quick access. So if it does any sort of maths or anything, it usually will sort of add two registers together and then either output the result in another register or potentially output it to RAM somewhere. So the term 8-bit or 16-bit computer usually refers to how many bits the CPU can read or write at any given time. Like I said, so most 8-bit computers, they could only sort of read or write like 1 byte at a time. and then there we go. I basically said that. So they could read or write a program from its memory map. So most computers, they kind of all of the random access memory chips or the read-only memory chips or any other sort of computer chip, they kind of have to be mapped to a kind of like memory map, which you can kind of think of as like a long street, if you like, and then each address can hold one number, and then this number would be a byte on an 8-bit computer, and then depending on if this address was on a RAM chip or on a read-only memory chip, depends whether you could write data to it or not. Obviously, if it's a read-only chip that's linked to some of these addresses on the memory map, then you can only read from it. So the two types of computer memory: random access memory, so it's only temporary, which means that if you turn the computer off, everything in RAM is usually erased, unless it's like a special sort of RAM chip, like the some of the consoles had, where they sort of like were battery backed up via like game saves. Otherwise, they would just be totally erased. So the CPU, it uses RAM to store data while the program is running. So the way these memory maps work is, it's like I said, it's like a street address. When you tell the computer to fetch a number from somewhere in memory for you, it kind of uses it as kind of like a lookup table. So it needs to know where it's going to first. So it kind of would like take a street number, would go to that address, take that number, and then pass it to you. That's probably the easiest way to kind of think of it. Obviously, if it's random access, then you can also tell it to store a number at that address, and then the computer will then put that number in the that location for you. So the differences with read-only memory is usually it's kind of like baked on the chip, if you like. So it's permanent memory. You can only read from it, not write to it. So ROM stores and instructions the computer needs to start up, and it stays even when the computer is powered off. Okay, not really start up, but. So this is like an example of things being mapped to the memory of the. This is a Game Boy here. Like, so most 8-bit computers, they had a memory map of 0 to. This number here is 65535 in hexadecimal. I'll describe hex more here. So in the above memory map, the numbers are used to represent the addresses. In this case, they're in hexadecimal, which is common when looking at memory maps for old computers. So binary is the language of computers. However, people need to work on a higher level. This higher level involves using the hexadecimal number system. So before I describe hexadecimal, I'll first describe decimal, which is the number we use. So I imagine that the reason why we use 10 is because we have like 10 appendages. So we have like a 10 fingers or 10 toes, you know. That's probably the reason why we came up with that. Like, so the distinct digits 0 to 9. And each position represents a power of 10. So the number 523 in decimal can be broken down as follows. So 5 is in the hundreds part here, which is 5 times 10 to the power of 2. So it's basically 5 times 10 times 10. This doesn't really matter if you get this or not. And then 10 is obviously 2 times 10 to the power of 1, which is just 2 times 10. And then 3 is obviously 3 times 10 to the power of 0. So everything is kind of based around tens, if you like, except the digits part, which obviously is units. If you've ever done sort of like, remember counting in primary school, like. So this is a base 10. This is what it's kind of referred to here. So decimal has 10 unique digits, so it's base 10. Each position is worth 10 times more than the position to its right. This is stuff I asked AI to give me an easy description of, to try and put it across. So this is what I said before. Base 10 is basically humans chose it 10 fingers. Binary is obviously base 2 because there's the switches that the computer uses, whereas hexadecimal is base 16. It works the same way kind of as decimal, except with different digits. So the way hexadecimal goes is it goes from 0 to 9, and then it also has A, B, C, D, E and F as the units, with F being 15. Then it starts at 10, which in hexadecimal is 16. So the hex number 11 here is 1 times 16 on the left here, and then this 1 on the right here is 1. So that's 17 in decimal. Doesn't matter too much whether you get hexadecimal at this point in time. Eventually you'll kind of become more used to working with it. When you're working with hexadecimal in C, you would normally use this here. So you put a 0, a small x, and then you would, in fact we need to put that as unsigned actually, otherwise it won't work. So there you go. The value of B there is 255 in hexadecimal. I'll cover the printf bit in a bit. So the above a memory map there, as I said, the FFFF. I'll show you the so there you go. FFFF is 65535. I'll be getting into these data types in a moment, so bear with me. So you might be asking, well, how do negative numbers, how does the computer actually know when a computer is negative? If it's only working with bytes, words, D words and Q words. Well, the answer to that is it kind of splits the number up. So what it does is when you have the bits here, so think of like an 8-bit number, so So in binary, so there's 8 of them there, like, so that would be 255. So if we wanted to represent a negative number, then we cannot use all of 8 of those bits. So what we have to do is we have to sacrifice one of those bits to represent the positive part and the negative part of the number, and then that gives us 7 to hold the actual value of the number then. So if this is on, then in fact I'm gonna have to so if it's on, then that represents a negative number there. So if I go for okay, why is it not doing that? Anyway, so it's kind of weird. So if you output a negative number, then, like I was saying, this bit here means it's a negative number, and then it kind of reverses everything. So -1 is actually that there, which would be 255 in hexadecimal, and then -2 would be that there, and then that there would be minus, what was it said there? There we go. So the negative range is minus 128 to 0 there. Don't worry too much about all this. This is just me kind of showing you all this now, so you kind of you kind of see some of the weirdness with computers. And then if we go back to -1 there, all we're interested in is just those last 2 numbers there. It should be just giving us those 2 there, but for some reason look, this is generating a 32-bit number there. If we do the same thing in here, it should hopefully not do that. Okay, it's doing that still there then. was trying to try and format it to just do 2 bytes, but it was having none of it for some reason. Okay, so the like I said, that one bit on the 8-bit number there, that kind of halves the range of that number. And then on a 16-bit number, you would still have the leftmost bit there, and then you would have 15 switches there. So that would give you, so if you think of the range of a 16-bit number, that would give you 32768, I believe. So that's kind of how negative numbers work. They're sort of like half the range of the number part, and then the 1 bit to the leftmost bit is then the sign bit, which determines whether it's a positive or a negative number. So we'll now get into, so what exactly is a computer program? Well, it's literally just a list of instructions for the computer there. So you see there, when we sort of code in C, everything sort of begins with a function called main. So a function is basically a name for a block of code. So for example, if we wanted to reuse some code to add 2 numbers together, for example, then we could do this here. And then this, whatever we these parameters which we passed in here, they would be what we'd be using to add together, and then it would then return this result. So for example, we could have in fact, that's not a good example there. I've missed a semicolon off somewhere. Oh, I've missed equals there. So there you go, 10 plus 20 gives us 30 there. So this is an example of a function. It's kind of like you would kind of describe it as like a block of code that you would reuse over and over again in your program. So normally a program would just, everything kind of in C needs to start or will start from a function called main. So a function, it normally returns a value. However, the void type here means that there is nothing returned. So you could have like a void function. So that's just an example there of passing a string to this function here. I'll explain more of what all of that is in a minute. So the C programming language basics there. So first off, there's kind of like three sort of like types of programming language. You kind of have the native language of the computer, which usually would be programmed in assembly language, but that's specific to a CPU type. So if you remember this picture here, so if you were back in the day, if you were coding for the Game Boy, you would be writing assembly code for the Sharp SM83 CPU, which I believe is very similar to the ZX81, I believe. And that if I show you an example of that there a moment. So when you were coding for these things, the instructions kind of looked something like this here. And normally to get these instructions, you kind of have to know what the number references to them were. So the assembly language usually has like these are known as mnemonics. So it's basically you end up with like commands which are really sort of basic. They usually are just like add one number to another number, or subtract one number from another number, or store or set one value to another value. They are really sort of low level. But the way that they're normally sort of coded is one instruction here, which is what they're known as, that usually has like a byte or a word associated with it, and then you would have like a following number. So that's assembly language is like it's the lowest form of coding. That doesn't mean that it's like a bad thing. It just means it's higher to sort of understand for us humans. On the plus side, it is extremely fast. Whereas the step above, a more sort of abstract or higher level, would be the compiled languages. So what happens in compiled languages is you kind of code everything in like a kind of text file here, if you like. So all of these commands here, they all sort of look kind of like English, and they all are understandable the more time you sort of spend with them. So what actually has to happen here is at some stage, all these functions and numbers that you put in here, this has to be converted into assembly language for the computer to actually understand it. And that process involves a program called a compiler. So once your program is finished, then you would need to compile it, and that just means that it converts the code into an assembly language program by reordering everything. On the plus side, you still might get the same speed as assembly, but on the older machines, it is kind of hard for computers to match a human programmer if the human programmer is good at coding for it. And then the languages above that are interpreted languages. So if you think of like well, what's actually happening here, this isn't actually proper C here. I believe anything you kind of do in the browser is kind of like a scripting language. So if you think of like scripting languages, or if you are familiar with like old basics on like the Commodore 64 or something like that. So if I open something here a minute, I can quickly show you what I'm talking about. So this is a Commodore 64 emulator here. So you can kind of type stuff in real time here. So this is an example of BASIC running here, and the way that BASIC works here is it's the sort of, as you sort of type stuff in, the computer is storing where this stuff is in memory as you kind of type it in the same sort of way that you type it there. And then what's actually happening is when you run this program, the computer is having to convert it into assembly language in real time, which is obviously a slow process. And languages like JavaScript, C#, Java, Python, and various others, they tend to have like an interpreter. Java and C# are kind of slightly different in that they have like virtual machines, which is another sort of program which converts your code into an intermediate code, and then it converts it into assembly language for whichever machine as you're running. So there's more sort of like steps in the whole sort of process, whereas if you're working with a compiled language, once you compile it at the beginning, it's then converted into an assembly language equivalent, so it should run at like the same speed as like a native program. Whereas the interpreted languages, when you go to run them, they have to be, they're not sort of converted in at the start. They get converted as they are actually running. So the interpreter has to take the in the case of this here, so it takes like a command, it then has to convert that as it's going along, and then send its converted instructions to the computer. The computer then executes those commands. The interpreter then goes on to the next line and then converts that into assembly instructions. which then gets sent to the computer and so on and so forth. Although the Java and C# now, and obviously on modern computers that run so fast, you wouldn't really notice any of that unless you were kind of doing like something hardcore, like the latest sort of graphics, if you like. So we'll now get into the C data types. You've probably, if you're not familiar with C, then you'll be wondering what I've actually been typing in here. So common C data types are kind of side by side. This here. So in C, we have unsigned numbers and signed numbers. So like I said, an unsigned number can hold the sort of like Intel equivalent. So an unsigned char here is the same as a byte in assembly language, as in it holds 8 bits and there is no sign bit. Whereas if you need to use a number that could be positive or negative, then you would use an unsigned char if the range of that data type was what you needed. So when you're working on like the Game Boy and stuff like that, you kind of, dependent on what you want to simulate, you need to kind of think first what the sort of maximum number range needs to be. So if it was going to be greater than 127 positive or less than minus 128, then you would go to the data type above that. So a char in C is usually a signed value. Whereas an unsigned char would hold just a number between 0 and 255. So what the printf function does is it allows us to output text in the terminal window or the console window if you're on Windows. So what these things here represent when we're printing text out is inside a printf command here. You have to put these double quotes, and then that means that you want to output everything that is within those double quotes there. However, if you want to kind of put numbers or insert other sort of text inside the sentence you wish to output, then you can use these special symbols here, which are the percentage symbol and then a special number or a special letter after that to indicate what data type you wish to put there. So in this case here, D, percentage D here means that you wish to substitute this symbol for a number, and then at the end of the printf function you pass in the parameters which will then be swapped in place for these symbols. So the first symbol here will take the first number here, the second symbol will then be replaced with the variable b here. So these are two 8-bit data types here. I'll show you another sort of function here called the size of command or function, and what that will do is tell you how many bytes a data type takes up. So you'll see here the size of A is 1 byte. So an unsigned short is a 16-bit number here. So if I tell the compiler to tell me how big the data type in C is, it should return 2. So an unsigned short holds 2 bytes there. So this is where things get a bit weird now. So when we go above shorts, the short data type, depending on the age of the compiler and the computer you're sort of coding on, some of the terminology that C had at the beginning was obviously relative to its age, if you like. So at the time there weren't 32-bit sort of computers around when it was first established, so the int data type could be a number with at least 16 bits associated with it. So for example, the size of an int when you code on the Game Boy is 2 bytes, whereas on a Game Boy Advance the size of an int is 32 bits. So that's something that I thought I'd sort of point out here. This is like a weird thing that sort of happens with it. And then you also get the same happen when you go for the long data type. That's sorry about that. It's tucked the that's totally screwed that up there. It does that. It read Inkscape sometimes it reads the keyboard when it shouldn't do. There we go. So as I was saying here, what I was going to do is I was going to show you the size of an int there. So you see that's 4 bytes there, and then if I turn that into a long, you see that's 8 bytes there. So that highlights the data types there. So basically the key takeaway is when you sort of when you're writing a program, think about what it is you kind of the range of something you need to store there. I get that at the moment you might be thinking, well, why? What do I need to actually store? That kind of depends on the sort of program you are sort of writing. So as I'd be sort of, all the stuff I'm doing is kind of game orientated. So what you'd be looking to simulate might be like a player type, or maybe a score or something. So you might do a game score, and then you might start that as 0, and you might have like player health, and you might say, well, that's 100 at the start. This might be a better way to sort of understand what you're actually looking to store here. And then you could have gun damage, say that's 50. So you look at it and think, well, maybe the player is not going to be able to do more than 100 gun damage. So I can change that to a char data type there. And maybe the health can go to a char as well. Whereas the game score, you might want that to be an unsigned integer there, because, well, that the player could score loads throughout the whole sort of time they were playing the game. These are probably better examples here of variables for our games. I was just using the others as like a quick way to kind of demonstrate code as I am going on. So one of the, as I said, this is the entry point into all C and C++ programs here. The main function. Normally you will find it with a return value. If it's got if it's got like an integer there, then it expects the main function block to return a number. So normally you would return 0 to indicate there's no errors. Any other number normally would indicate that there was an error. And then I will now get to what this actually means here. So the C language itself, it consists of various like core commands, if you like, but they are stored in a number of different libraries. So I will now show you a link which I use. Let's open that in another tab. And then what this does, this link here, is it has a list of all of the standard C libraries here. The names are the ones on the right here. So math.h, stdint.h. The ones on the left are the C++ equivalents. So you would see that this includes the stdio.h library. And then if you want to know what's in there, you click on that, and then it tells you this is for various input and output operations. So you can use it to read or write like files, and writing text to the console window is classed as an input-output method as well. So if we have a look in the printf function here, you'll see it returns a data type int, and then it expects a const char pointer. So a const char pointer, basically in C, this data type here is what you would call a string. If you've used any other sort of programming language, then you would know what a string is. A string is basically a name given to a load of text. And the reason it's called that is because you see that it says data type char. And that's because this is basically a list of chars. It puts them all together for us. And then using the printf function, we can pass in this special command here. The I'll zoom in here a minute. The %s just means replace this symbol for a string, which is a const char pointer here. What this actually means is this is pointing to the memory area where this string of chars is actually stored. Hopefully that kind of makes sense to you. So it lists here, you see what I've been doing here. This tells you the what's actually expected here. So you see const char pointer here. And then these 3 dots here, they just tell you that the this function takes any number of arguments after the format bit here, as it says here. So when the printf function scans the contents you've passed in, it looks over this, it has its own const char, and then what it does is whenever it finds a percentage symbol, it then sees what letter is after it. So for example, if you pass in a percentage symbol and a D or an I, it will take a parameter after the const char pointer that you passed in, and then it will substitute that with a number here. So this is our text here. If I do a space afterwards and I put %i, then I can put a number after there, and you see it's substituted %i for 65. So if I put you see it's put in our text there, and then at the end there it's substituted that symbol for 500 there. So using the printf function here, we can not only output text, but we can also pass in custom variables in here. So that's what these things are here. So So what we're doing here is we are taking our variable my score here, and then we're telling the computer to add 10 to the value of it. It's because so you see there it's added 10 to it, so as it's an integer there, we could even do that there. And I'll show you another thing you can do as well. So, or maybe you've just hit something that's lost you some score. So you'll see now my score is minus 100 there. So the I or D symbol does exactly the same there. So if we wanted to output it as an unsigned hexadecimal integer, then we can substitute the D for an X. So you'll see that the lowercase x puts everything in lowercase here. If you use an uppercase x, do the same again, you'll see it outputs it in uppercase there. So if you wanted to use the printf function or any of the other functions which are in the stdio library, then you must first include the header file for it. So if I'll get to some more in a moment here. So these symbols here basically allow you to substitute these symbols inside the string that you pass. So you see here there's also the flags bit here. And then there's also the dot precision as well, which is what I was trying to force earlier. So earlier when you saw that, I was so let's give another example here. So we'll say our health is at 100. In fact, no, we'll say our health is, so that I'll show you in assembly what I was actually trying to do here. Sorry, hexadecimal. So our health is 255. So that's worked there. So if I put that to a minus number here, so it seems to ignore that and forces it onto that's irritating there. I didn't realise it forced that to. So when it's a negative number, it kind of automatically converts this. to an int for some reason. So let's change this here and see where that makes a difference. So it does it then, but it will not shorten it for some reason. So you'll see here, because I've put .2x here, what this should be doing is it's saying take this number and output it as 2 digits. So if I put that as 3 there, yeah, so it's growing it. So as an example here, so if I was outputting your score, then I might say force the force that to like 5 numbers or something. Oh, it's because it's turning it into a negative number again. That seems to throw it off. So it only works with if the number is positive, it seems here. So it says here the value is shorter, then the result is padded with zeros. Whereas it will not shorten it if it's longer. That's what it's basically saying here. I wonder if we need to push these in here as well. Let's see whether that works. So normally I wouldn't, I probably wouldn't be outputting large negative numbers in games anyway, but this is just to kind of showcase some of this here. So let's say our health is that -9. Let's see if that will make a difference. No, that's not what we're going for. Okay, that's worked. So I'll tell you what, this is the health thing has actually worked there. So if I remove all of these other things here a minute, and then I'll explain this line here. So this is something I sort of come across the other day here. I normally, if I was working on the desktop, then I would be using the commands as they are here. Normally I would just stick everything as integers if I was coding for the desktop. Whereas when you're sort of coding on the consoles, you try and pick the correct size data type which the number will fit in. So if I side by side this a moment here, so one of the things I noticed the other day was some stuff was not working as I was expecting them to work, and that's because I was using data types which was not an int. So in the printf parameters, when you are working with parameters that are not integers, as in they're not the int data type, then sometimes you have to pass in additional precision symbols here. I believe it's what it's saying they are. No, sorry, it's the length. So this is the precision bit I want here. So I'm saying force this to 2 bytes. And then this bit here is the length sub-specifier. I'd never used this before, and then the this HH here says that the data type we're passing in is a char here. And then if you're working with a short, so we'll put that in here as well. We'll say our range for our gun or something is -256. So we want to print out what our range is there. Obviously we can't do so we'll print that out first as in hexadecimal there, just using that. So you see what it's given us there is it's given us an unsigned int there. It's rounded this up to an integer here, which is not what we want. So to get this to short, we will use the H one there. And now you see that that's correctly formatted it. So that's 1 byte and that's 2 bytes there. So this is that's also -256 in hexadecimal there. So if you are not getting what you expect to be getting, or you're passing in different variable types here telling printf to output it, it might be that you need to add in one of these length things here. The irritating thing is that if you go down to the examples here, I don't think there's really anything which you get one example here, but it doesn't really sort of go into using any of these here. So I thought that I would share this one with you, as it sort of caught me out, because normally on the desktop I would be storing all my numbers as ints, because the desktop, obviously you don't have any real sort of restrictions memory wise or CPU wise. So I will now get back to here a moment. So I've showed you some data types here, some examples of them. And then I zoom back into this a moment. Come on. There we go. So you can think of in your game anything that you need to sort of represent as numbers. That's what you would use a variable for. So for example, we could have these variables here. So penguin equals 5, So what we're doing there is the 5 value is being assigned into our variable penguin. The reason why we've chosen integer for it is because if we come up here, we expect the value of penguin to rise to greater than the range that a short or a char could hold. We chose a short for our variable fish, as the possible values that it can hold will fit nicely inside a short data type. And then the char for plankton here. So we use the equal symbol here to tell C to assign a value to our variable. And then every sort of command we give, we have to pass a semicolon at the end there to signify that that is the end of the line. So if I come back here, and then you'll see that if I forget to add a semicolon there, then we get this error here. And then it says line, the number there means line 15, although the error is obviously before there. So sometimes when you're sort of this is going to be a really common one which you'll get. You output in loads of info, and then you forget to put a semicolon in there. So when you're starting out, do a few lines, compile, do a few lines, compile, just to make sure your code properly builds. Otherwise you'll be going through it trying to figure out where the missing semicolon is potentially. So other things we can do here is, so not only can we add, but we can obviously subtract as well. So to add two numbers together, so if I take the score variable here, you could do my score equal, and you say take the value of it and add 10 to it. A shorthand version of that is my score, and you say plus equals. That basically does exactly the same, except you don't need to write the variable name out again. A compiler will understand that as my score equals my score plus 10. So if we output the value of my score now, so you'll see here, we'll put the start to 10. I'll move that line there as we don't need it now. So there we go, started at 10, we added another 10 to it there, take it to 20, added another 10 to it there, take it to 30. So we could just as easily as substituted that there. And then we can do the same with the minus symbol there. And then that will do subtraction for us there. So we took 5 on this line and then took 5 on that line. Now to do multiply, you have to use the star symbol. So if you wanted to times that by 2, you could either do my score equals my score times 2. That's what that star value signifies. Or times equals 2. So that's how you can multiply a value. So the next one is divide. To divide something, you use the backslash there, or sorry, forward slash I think it was called. And then that will divide that by 2. And then when you are doing maths functions, so you could say my score equals so what happens here is everything in the brackets is worked out first, and then everything outside the brackets is then calculated. That's one thing to be aware of when you are doing calculations, is you can add brackets to parts of the calculation, and then that will get added up or calculated first. So another thing to explain to you here so there we go, there's our number there. So what do you think will happen if I subtract 6 from that number? It's an unsigned number, so it can't be negative. So what actually happens is when you add or subtract a number, so as we've got the as my number here is a char data type, if it goes outside of the range that that data type can hold, then it will wrap around on itself. So I'll demonstrate that here using a for loop. So what this is going to do here is this block of code will be run 10 times. And then this will show you what happens to the value of my number. So you see, first off, its value is 5, then it's 4, and then it goes to 0, and then it loops back to the top. So that's one thing to be aware of. You won't get an error here. It will just loop back around. So sometimes that can be a good thing, but other times that can be that can lead to weird outcomes for you when you don't expect it. So you'll get the same outcome here with if we change that to an unsigned short there, do the same again, you see that loops back around to the top there of the range of an unsigned short. So that's what happens when you add or subtract to unsigned numbers there. If you don't sort of prevent them from looping around, then they will. Whereas this will be totally different if you had a signed number there. So you'll see now that the signed number behaves as you expect it. It's gone into the negative range there. So I'll also explain this here now as well, and this here. So there's two different ways you can also say add 1. So you can say add 1 to my number like that, or add 1 to my number like that. And these will give you two different outcomes, believe it or not. So I will now show you the post addition here. So what will happen here is the number will be printed out first before 1 is added to it here. So you see we start at 0 here, and then we count up to 10 in here. This symbol means less than. That's like a logical sort of compare symbol when you are sort of working with like a counting. So if we change that to pre-addition here and run that, you'll see that it adds 1 to this value before the printf substitutes this symbol for it. Just thought that would be something you might want to sort of be aware of there. And then this stuff here, this just means do whatever code is inside this block here for less than this many times. I'll cover loops and stuff in a future video. However, they will be potentially present in some other programs before then. It's just a part of the coding thing here, I'm afraid. So we will now get back to this here now. So I've gone over the multiply, divide. I've told you about the printf function here, which I kind of thought was you kind of have to put it in a tutorial, because otherwise it would be pointless having addition, subtraction without you being able to see the results of it, you know. So that it kind of has to kind of be in there. This is the printf. It's kind of the only sort of main one I will sort of cover here, although I will actually be using a few more in a moment. So those are the key things I wanted to cover in this video here. So now let's do some fun things. So now we will go over the first program here. So this is our first game here. You see here I've included a few more libraries in here now. And that is because of the additional functions I will be using now. So another thing we can do in your programs is, if you have a constant value that will not change in your game or your program, which you will want to reuse over and over again, and maybe you might want to change that value at one point. So it could be that we have our max value here at 30, but maybe later on we want to change that number. Well, rather than type out 30 all over your program, we can just define a constant value and give it the number 30. And then wherever that value is in your code, if you decide to change it later on, you only need to change it in one place, which is where the define statement is. So this says define the variable here with this value here. Notice that you don't need to put a semicolon here or even an equal sign. Anything with a hash or a pound symbol, as it's called, I believe in American, anything with that is a special sort of command. So this program here, I'll run it here and I'll play it first off, and then I'll tell you how it all works. So this is the number guessing game here. So this is to kind of give you a game to play, so you can kind of have a base to muck around with. So this will kind of introduce these data types here and kind of hopefully make the learning and playing around a more fun process. So the computer's asking us to guess a number between 1 and 30 here. So let's do that. So we've got that wrong. So the number that it's got is higher than our guess. So let's go with 25. And it's saying nope, it's higher still. So let's go with 28. Still higher. There we go. We've correctly guessed it. So that took us 3 turns, and the number that it had was 29 there. So I will introduce you to some more functions here. So this function here is called srand, and what this does is, this is in the standard lib library here. So if we want to work with random numbers, which you will in most of your games, otherwise it'd be dead boring if it was the same number every time, we can get the computer to generate random numbers for us. And one way to do that is to use the srand function, and then we pass in this time function here, and then this goes off of the system clock in your computer to seed a random number generator. Basically what that means is it gives it a starting number, because they have to have a starting number to base there's like a calculation that the computer does, where it will add one number to an arbitrary number that it has, and it will continually do that over and over again, which will seemingly give us a random number. However, if you put in the same seeding number, you would potentially get the same sequence of random numbers back. Anyway, let's have a look at the srand function here. So here we go. This initializes the random number generator. So this tells you what you need to pass in there. So you pass in an unsigned integer, and then it gives you an example here of how to start it off. which is exactly what we are doing here. So you need the time header here, and you see there's a time function here, and then you'll see that the time function just gets the current time, but it expects you to pass in a data type, time t, as a pointer. However, if you pass in null, then that is also a valid value as well. Basically, there's a data type which is called a null pointer, which basically is the same as passing in 0 there. Don't worry too much about this here at this time. The key thing is that this command here requires the time header and the standard lib header there. So this initializes internally in the program the random number generator. Once it's been initialized, you can use this command here, the rand command. This brings me on to this symbol here now. So if I open another instance of this here, so this symbol here, when it comes to like maths here, what this means is divide the number in n by 5 and give us the remainder in p. So this is called the modulo operator. You'll see it in the rand functions. It is fairly useful if you need to know what the remainder of a division is. One thing you can also use it for is it means that whatever number is in n, it will be clamped between 0 and 5. In fact, let's do some testing here to make sure. Oh, we've not printed it out. Bear with me. So it will be between 0 and 4. So if you put 5 there, then it should return 0. There you go. So if you do that, it will still be between 0 and 5. Oh, sorry, 0 and 4. This could take this browser one a bit of a time to work out that actually. Okay, let's stop that. I don't want to be here all morning. So now what this is doing is this is clamping any number you put in here to be between 0 and 8. There you go. So that's the modulo operator there. Like, now the reason why you would use that with a random the rand function here is so that it will take the number that it generates here, and it will make sure that the output number is only within the maximum range number that you specify here. So you say, give me a random number between 1 and whatever. So in our case here, it's a random number between 0 and 29. This is what this actually ends up doing here. And then because this number will be between 0 and 29, we add 1 to it here. And then what we have here, so in all games you end up with what's called a main game loop. Basically you say run this game until the player says quit. That's kind of how it goes. Or you say run this game until the player has lost all their lives, or something to that effect there. So another thing we've included here is the standard bool header here. And what this does is it introduces another data type called a boolean, and this data type can either be true or false. It only has 2 states. You think of it as just like a switch. It can either be on or off, so true or false. So in our case here, anything you set outside of the main function here means that it's a global variable to the module that it's actually inside. So in the case of, if I open this up in here, so this program here in code blocks, main.c is what's called a module. And any variable that is declared outside of the module, so outside of a function block, is considered a global variable inside that module. So say penguin equals 5 there, and then we have another function here saying so if we build this and run this a moment, you see it says there my number is 5 and your number is 55. So the value of penguin here is 5. and the number we've passed into this function is 55. So the program already was aware of Penguin. Now if we do this, so what I've just done there is I've commented this out here. So sometimes when you're programming, you'll have some of the code that you've just typed out, but you might want to test something else out. So one way to keep your existing code, or maybe to even give some pointers to yourself, as in you say this function outputs a number. So maybe you want to document what each of the bits of code do in your program. So this is what you would use a comment for. You can either use it for adding comments to your code to assist yourself when you look at it in the future. Because if you don't have these, there's a chance that if you spend some time away from your program, when you come back, you might not remember how it actually works, which is possible. So what we've done here is we've commented this declaration of Penguin out here, and instead we've moved it inside the main block here. So what will happen now is this will generate an error, and the reason for that is because this Penguin variable is only declared locally in this code block. So this code block is not able to see it now. So this is what's called scope, which is how you can reuse a variable potentially. So you see here, although we've declared Penguin inside here as 9, this code block here, this doesn't recognize this Penguin here. It only recognizes the global Penguin outside here. So what am I on about now? Yep, back to this tutorial here. So the Boolean can only be true or false here. So inside our main game loop here, we first tell the player, well, we ask them first, can you guess my number? So what this symbol here does is it says create a new line in the output window. So if I come back to here, and then let's try and find where these things are a minute. There's a whole list of useful symbols here. So it's not in here. Where are they? Not sure if it's in scanf or not, which is a function we need to cover in a moment. There's a table somewhere in here of the special characters. It's in here. I can't remember where it is now, but then there's a load of special characters which have like a /n, or there's like there's various other letters here. So there's certain symbols that you can and can't print. So if, for example, you think, well, how can I print out the quote symbol there? And the way that you do that is with a slash and a quote. See that there's a quote there. And then if you want to print out a slash, then you have to put two of them in. Okay, maybe is it 3? Yeah, so I'm sure it is only 2. Yeah, so you kind of need, if you want to put like a backslash there, you need to put 2 of them in there. So that does new line. Ah, wait there a minute. So loads of those slashes, they kind of correspond to some of these things here. So /n is new line. No, it's not got the symbols there. Sure, I've got those somewhere. So anytime you kind of want to do like a line feed in the console window. So for example, if we come back here a moment and then so what that should do is it should start everything off with a load of spaces. I don't know if this is working or not. Let's try again. There we go. So there's a load of spaces there at the start there. So anytime you need to create some extra space in the output window there, /n will give you a new line. Anyway, back to our code here. So here we just say, can you guess my number? Then the next line here we say it's between 1 and then max value. So you can change this. So we change that to 10 there, run it again. So now the number is now between 1 and 10. So let's 5. It's higher than that. It's 9. Oh, there we go. First time, almost. So that just, we print out there and we tell the player what range they need to guess within. Now this command here, scanf, what this does is this allows us to read some text or numbers from the command line. So the printf outputs text to the command window, and scanf will read text or numbers. Basically, it reads input from the command window. So what we define here is we define a char data type to hold the return value that the player will pass to us. If you come in here and then have a look at scanf, which is in stdio here, you'll see that it kind of the function parameters here look pretty much exactly the same as printf. The only difference is the parameters in here now in the format string which you pass, they are read now from the command line and they're passed into these variables that you pass in there. So one thing to note is normally whenever scanf finds like a white space character, like a space or enter or anything else, it will then stop it will stop reading the data from the command line. And then you'll see here the specifiers look exactly the same as the printf. And then you'll see here in scanf here. So if you want to read in a number, you have to add this and or ampersand symbol before your variable name. So what this does is it doesn't actually pass your variable, it passes the memory location. That symbol says pass the memory location or get the memory location of the variable, which is why I was talking about RAM earlier and computer memory. Because all these variables which we declare, they are stored somewhere in the computer's RAM. So you see again, just like we were in the previous program when we were trying to print out a char, we needed this symbol here. It's exactly the same when you're reading in some data. So another thing to bear in mind as well is what number you're reading in. What's the range of that number going to be? You can throw this out. There's no sort of error checking in this program here. If you put in too high a number, so if we run this again, and it actually works. So our number there is a char, so it can't hold that there. Okay, I wasn't sure what the result of that was actually going to be there. So it's kind of converted it into a char by the looks of it. So because it's higher, it's just wrapped it around automatically. Wasn't sure what the result of that was going to be. So this here is obviously clamping the data read into a char for us. If you remove this, then the program runs, but not as expected. The logic doesn't work anymore, weirdly. It took me a while to figure out I needed to put that there. So if you changed the your number there to a short, then as before, you would change that to a H instead. If it's an int or above, or rather if it's an int, then you don't need to do anything because C for the desktop works with standard ints anyway and treats them as 32-bit numbers. If you were working with a larger value though, or variable, then you would potentially need to pass in the LL for a 64-bit number. So what this does here is it reads in a number and then it takes the value we've inputted on the command line and puts it inside our guess here. What this command does here is this is a comparison block. So what this is saying here is if the number in your guess is equal to the number in my number, then execute this code here. Else, execute whatever code is in here. So these are if-else blocks here. Won't go into much more detail in here, but another thing to, I guess I'll have to kind of go in the comparison operators here. So if you want to compare two numbers against each other, there are a number of ways you can do that in C. So we have the greater than symbol. So if the value on the left hand side here is greater than the value on the right hand side here, then this is true. So the code inside the curly braces block here will be executed. What this symbol means is it means that B is greater than N. So this is saying that if N is less than the value of B, then execute the code inside here. What you can also have is you can have equal to or less than. In fact, I might have got those around the wrong way there, so we'll open another window there just to make sure. So I'll show you these. So we'll have int t is 100 and int b is 80. So is t greater than b? Copy and paste that in there for good measure. There we go. So let's put the value, output the value so you can see it there as well. Ah, I didn't put the values there. So that's one thing to note there as well. Sometimes the program will still run even if you don't include the variables for it to print out. However, it will be buggy. There we go. So t is greater than b. So let's set that to 800 there. Run that. So there you go. Look. T is less than b now. So what do you think will happen now? So these only check to see whether one value is greater than the other. If you want to check for greater than or equal, then you do this one here. T is greater than or equal to b. So we'll put a new line there. As these are all separated here, I'm expecting both. In fact, if I do this, both of those should run. There we go. Look. So t is greater than b, 805. If we set them both to equal again and run that, and you'll see here the could be the same or greater. So let's do that one again there, and I'll show you how you can link these compares together here. So you can create like a whole chain of these if comparisons here. So this time round, because these are linked together, only one of these will actually fire, will be executed, which is the first one there. Now another thing you can do is you can chain in a final sort of compare there. So what will happen is if we put that to 25 there, there you go, let t is not greater or equal. So you can chain these here. So what will actually happen is these three blocks will be tested to see which one actually fits, and only one of these will be run. Whether if you had them all separate, then all of them will be run. So that one is, this one here is fired here. Is it equal to or smaller than or equal to? Let's see. Nope, it's not. try that again. I'm wondering if it's because I have like another instance in the browser of this or not. Okay, let's stop doing stuff in the browser now. There we go. So t is greater or equal. Sorry, t. It could be the same or greater. So this one here, and then also the bottom one here, which is what I expected to actually happen there. So using the if, else, or else ifs here, you can do a whole load of checks for your variables to establish directly what ranges they are in. So that sums up, in fact no, we still haven't finished it yet. Let's get back to the browser here. Okay, so outside of here, the computer generated its number in rand. We then get the player's guess. If the player's guess is equal to the computer's number, then we print correct. And then you'll see here the boolean for ending the game is false. So what this means is this, all of this here will keep looping while the B game end value is false. So if the guess is incorrect, we add 1 to the try count, tell the player it's incorrect, try again. We tell them what number they guessed so that they know not to use the same number again next time. We then check to see whether the computer's number is greater than the player's guess. If it is, we tell them that the computer's number is higher, else the computer's number must be lower. And then if the player gets the guess correct, we set the end game value to true. This then ends this block of code here. We then finally print well done, you guessed. Your try count turns, which is what's happening here. And then we say the that's right, the number was this here. And then at the end, before the program executes or finishes, we use this command here to read one character from the input line. So if you build this in the compiler here, so if you build this in here, then what you've actually generated, if we try and find where that actually is, so this here you should be able to send to someone if they've got Linux, or if you build it on Windows you'll end up with an exe file. And then in Linux, if you navigate to where that is, then you can run it in a terminal window, or they can run it in a terminal window, and then you can play it there. Likewise on Windows, if you navigate to where you built it, then you could share that the output program with someone, as long as in the settings, so in your project, if you go to build options, make sure you statically link libgcc first. And then what that will do is that will include the C library that's used with mingw or GCC into the exe file, so that they shouldn't need to have anything installed on their computer. So you see here, this only takes up 14k of RAM here, so you could easily email that to someone to play. So that's the number guessing game there. So the next game is the silly story game. This one's a bit more complicated. This one takes in some strings. So we have an additional library here now. This is the string H library, which we use for various string and memory copying operations. So this time, if you want to store any like text which people are typing in on the command line, then you need to store them as what's called an array of chars. So just like the const char pointer that printf takes, you can think of these as equivalents which are in RAM, if you like. Now that might not be a good analogy. I kind of don't want to go into what arrays are, but this you might need to hear. So basically, to create like a whole string of text here, each of these letters takes up one char. So if we want a whole sentence, we need to create like a large bucket to keep them in. So the way that we do that is we create what's called an array. So you could have like, if you wanted, say, if you wanted 20 integers to be all in like a group or a list, then you define what's called an array. I didn't really want to touch them in this video, but I feel obliged to, because I'm obviously creating arrays of chars here for sentences. The reasons why you would do this with numbers, I will go over in a future video. So for now, what this program does here, if we run this here, I don't think there's any way I can kind of, now I can't sort of scale it. So this program here, it just it says just answer more questions, and I will give you a story based on what you say. So you put in your name, so give a random name. So give it some random stuff, and then it will come up with a story at the end there. So it says, based on the information I passed, once upon a time there's a person called Gerald. They're 55 years old. Gerald lives on Mars. They had a pet which was a penguin. It was 152 years old and it liked to eat iron. If it was not eating, it would be doing its favourite thing, flying in space. And it says, I hope you like my story. So what this program demonstrates here is how to construct a mini story, if you like, from the player. So you've already seen the printf functions before, so there's no reason for me to explain them here. The only thing which is new really is the scanf function taken in a string of chars. So depending on how long your sentences are, you might need to increase this here. So if you wanted to include loads of other sort of text for various questions you were going to ask the player, then you just need to create more char arrays. And then here we are using this here to keep all of our strings at a constant length. So they can't be more than 20 characters in length. So what this function here does is we use, what I'll do is I'll close this here. So we're back to scanf again here. And like I said before, one of the things that scanf does is it ends reading stuff in if it finds a space or anything that's kind of not really considered a letter. So the %s tells scanf that we're going to read in a string, and then this special definition here so you'll see here these brackets with this to the power of symbol says negated characters here. So basically don't end if you find any of these. That's what it's kind of doing here. So it's not going to end until it finds the end of the line here. So /n is a new line. So this will allow us to kind of type in multiple letters and spaces. And then we also need to make sure the start of the sentence has a space as well. Otherwise this won't work correctly either. So whenever we have this block here, I don't know if we can remove that. Let's see whether that works. No, that broke it there. See, look, it's split this up, and the return results, it's passed into multiple lines there. So it does need those brackets in there. So the first one here, we take in the name, then we take in the age. Notice here that I decided to use integers instead of shorts or chars. Again, we could have used shorts or chars, but then you would have to put in the other special characters to tell scanf that we are not using an int to store things in. And then more of the same here. We read in various strings and numbers, and then at the end here we use a for loop to print out some new lines there. That's what this is doing. So you'll see in these for loops we basically create like a local variable n, and then we say run the code in here while the value of n is smaller than 5. So it's almost put in like 3 maths equations into the for loop start here. So you could also do this instead, and it will do exactly this sort of same. And then at the end there we just print out the results. So you've already seen, I've already sort of explained these here. So the percentage %s will print out a string. The only difference here is instead of a const char array or a const char pointer, so what this actually means here is this symbol here basically means a load of chars, or maybe one char. So this here basically is the same as passing like an array of chars. So you can kind of substitute one for the other. So that is the silly story one there. I'll leave these as like a load of text files like this, so you can literally just copy and paste them in. This one here is the most in-depth game here, so this is the one I'll leave you with. I will quickly explain this one here, and then we will call it a day. So this one's the more interesting one here. So the new things, which I'll point out. So we have a name for our hero here, and then we have some attributes of our hero. So we store their speed, the hero's attack, and the hero's health, and then we have another string which will hold the name of a monster. And what we've declared here is we've declared some const strings. So notice these here are predefined with letters already, and these are constant char pointers, whereas a string array of chars without a default value are not const. What this means is these values are constant. so they can't be changed. Whereas these can be changed. So these are some monster types. So you'll see here, I've only created 4 monster types. You could add another one in here if you want. Just use the same sort of naming convention. So let me think, what should we have? Let's have dragon, and then we will increase that to 5 monsters. And then one thing that we've included here is we've put in, although these aren't really used directly, I've created some functions which make working with rand easier. So we have the rand function here, which basically we pass in one maximum value and then it will return an integer already formatted by rand there. This one here though, this one's slightly different. We can get our numbers now between a minimum range and a maximum range here. And this shows you how you can achieve that. First you take the maximum range as you would with a normal rand. You then add the minimum value to it. If the value is greater than the maximum value, then you clamp it to the maximum value. That can be in return that. So this allows you now to create a random number between 2 ranges. And then here we have another function which basically formats the random range inside of it to between 1 and 6. So this simulates a one-sided dice with 6 faces here for us. And then we have some functions here. This one here will make our monster. So the monster, we only fight one monster in this battle, and it can be, we want to include a new one here now. So if you include any new monsters, then you will need to add them here into the if and else if block here. So what's happening here, there's a function in the string.h called strncpy. So if I come in here, so there are some functions for working with strings here. See which one is it we are using. So we are using this one here to copy a string. However, a better version would be to use this one here. As this one here, you pass in the maximum size of the destination char pointer or char array, so that you can't try and put in or copy too many letters from one string to the other. So I will substitute that now actually. So we'll use that one instead, and then we'll say string name max. So this will clamp the amount of letters and stop the monster's name string from overflowing. So we actually want to pass in -1 there, because there's actually a hidden character in all of these strings here. They kind of have to end with the value 0 at the end of the string, otherwise they will generate an error. So let's just format those here for us already. So what these are doing here is this is our empty monster name string here, which has 20 chars. And depending on the random number which is returned to our monster type here, depends what name of monster we copy into the monster name string. So you'll see here, these are all the names that a monster could be. So depending on the random number, depends on which string we copy in here. We then roll a 6 for the monster's attack, roll another 6 for its speed, roll another 6 and add 10 to it for its health. And then to make the hero, we do exactly the same, except we give our hero an extra 5 health. And then we have a function for when our hero attacks the monster. So we roll a 6 and then we store that in player roll number here. We then add the player's attack value to that. That is the value or the damage that we will do to the monster's health. And then when the hero attacks, that is, and then we say that the hero hit the monster and did player roll damage. We then subtract the player's roll damage from the monster's health. If the monster's health is less than or equal to 0, then you've killed the monster, game is over, and the hero has won. When the monster attacks, we basically do the same but for the monster. And obviously if the hero's health goes less or equal to 0, then we tell the player that they was killed by the monster. We have some local variables in here. We keep track of the rounds that the battle have gone on for. And then before we go into the main game loop here, which is another do while loop. So this here is the same as saying equals false. There's a number of ways you can have false or true in the comparisons here. So that is also false, or sorry, that is also false. So what this exclamation marker means is not. So that means not equal to true. That there means game over is not equal to true. So that there is the same as that there. So while it's not game over, we basically run this loop here. So before we play anything here, we set up the hero and the monster, so they're both generated randomly. We then tell the player the specs that the hero has and the monster has. So what I'll do is I'll actually run this here before we go any further. So what is your name? And we'll say Conan. So Conan will be facing the giant spider. So Conan's health is 20, speed is 1 and attack 4. The monster has a higher speed and a higher attack, so that's not looking good. So we then go through each round there where it says round 1 fight. So we've got 20 health left. The spider's got 11 health left. The spider just hit us, doing 10 damage. And then just press return each time to go through each round of the battle here. So the spiders hit us again there. Oh, the spiders killed us there. We've died. And then game over there. So what we do here is we basically use the get char function there to wait for one key being pressed. Then once that's pressed, we're not interested in the value that's returned there, then we basically update the battle round number. We roll a 6 for the player, we roll a 6 for the monster. We add the player's speed to the player's roll and the monster's speed to the monster's roll. And we say whoever got the higher number is the person or the monster that strikes first. If they're both equal, then they both have a chance to hit. And then this just continues until the game is over. And then at the end we pause for another key press there. So that is it for my first video. Hopefully you found that useful and it will help you. And if you have any comments or questions, then leave them below. And I will catch you in the next video. Thanks for watching.